Hi there, I'm Jeremy Krug, and this is my 10-minute review of AP Chemistry Unit 8, covering acids and bases. Hit that subscribe button if you haven't done so already, and share this video with the other members of your AP Chem community. And don't forget that if you want the best AP Chem review experience out there, head over to ultimatereviewpacket.com and get all the review you need, along with 2 full-length exams, hundreds of practice questions, and the full guided notes for my YouTube video course. Now, let's get started. We use pH and pOH to discuss concentrations of hydronium and hydroxide ions in solution. pH equals negative log of the hydronium ion concentration, and pOH equals negative log of the hydroxide ion concentration. Just so you know, we often use H+ and hydronium interchangeably. At 25 degrees Celsius, the concentration of hydronium ions in an aqueous solution times the concentration of hydroxide ions always equals 1 times 10 to the negative 14th power. We call that product Kw. Another way of saying this is that pH plus pOH equals 14. So that means that with these 2 equations, if we know any one of the 4 values, we can calculate the other 3. Anytime that pH equals pOH in a solution, the solution is neutral. At 25 degrees Celsius, neutral means a pH and pOH of 7.00. Acidic pH values are lower than that, and basic pH values are higher. Just like any equilibrium constant, when you change the temperature, you change the constant. So at warmer temperatures, the Kw value goes up. So pure water at higher temperatures has a pH a little lower than 7, but it's still neutral. We can say the opposite for colder temperatures. There are 6 strong acids, and we can calculate their pH values very easily. Since strong acids ionize completely, the hydronium ion concentration is equal to the concentration of the acid. So to find pH, just take negative log of the concentration of the acid. So the pH of 0.010 molar nitric acid is just negative log of 0.010, which is 2.00. Strong bases are done the same way, except it's pOH. Group 1 and 2 hydroxides are the strong bases. Just take negative log of the hydroxide concentration to find the pOH, and then subtract from 14 to get the pH. With the group 2 hydroxides, remember, there's a 2-to-1 ratio. So in the case of 0.01 molar calcium hydroxide, you'd take the negative log of 0.020 to find pOH. Then subtract from 14 and you see the pH is 12.30. For weak acids, we have to write their dissociation as a reversible reaction, which is an equilibrium. So in the case of hydrofluoric acid, its dissociation looks like this. As a reversible reaction, it has an equilibrium constant, which we call its Ka. Sometimes for convenience, we calculate its pKa, which is just the negative log of Ka. It works the same way for a weak base, except it reacts with water to form the conjugate acid and hydroxide ions, and its constant is called Kb. Likewise, pKb is the negative log of Kb. To find the pH of a 0.50 molar solution of hydrofluoric acid, we set up an ice box, just like we do for any equilibrium problem. The initial concentrations of our products are essentially 0, and then we use X for our change. We then plug the equilibrium values into the equilibrium expression and use algebra to solve for X. Since we have a small equilibrium constant, we can ignore X to save time and make our math simpler. The pH is just negative log of the hydronium concentration. The percent dissociation is the X value divided by the initial acid concentration multiplied by 100, like we see here. When strong acids and strong bases are mixed, the net ionic reaction is always the same. If the moles of acid and base are equal, and we're at 25 degrees Celsius, the pH should be 7. If one of them is in excess, you can use moles of excess reactant and total volume to calculate the pH. If a weak acid and strong base are mixed, you'll produce water and the conjugate base. If there's more weak acid than hydroxide, notice that you'll have a mix of weak acid and its conjugate base, which we call a buffer. More about those later. When you mix a strong acid and a weak base, you produce water and the conjugate acid. If you have more weak base than hydronium, you have a buffer solution again. Now, in both of those cases, what happens if you end up with more hydronium than weak base, or more hydroxide than weak acid? Then you work the problem as a strong base or strong acid problem, just like we did earlier. If you ever combine a weak acid and a weak base, compare the Ka of the acid to the Kb of the base. Whichever one has a larger magnitude will tell you if the resulting equimolar solution will be slightly acidic or slightly basic. For acid-base titrations, we can use this equation to determine the concentration of the acid or base, or the volume required to get to the equivalence point. We use a titration curve to plot the volume of titrant added from the burette on the x-axis and the pH of the mixture on the y-axis. For any titration curve, the inflection point represents the equivalence point, the moment where moles of base equal moles of acid reacted in the mixture. We can look at this graph and say that this is a weak acid being titrated with a strong base, since the equivalence point is a little greater than 7. One of the most important parts of a titration curve is the half equivalence point, because at the half equivalence point, the pH equals the pKa of any weak acid involved in the titration. And we look at the halfway point and estimate the pKa of this acid is about 3.3. For polyprotic acids, the number of inflection points tells you the number of acidic hydrogens in the acid. With 2 inflection points, there are also 2 half equivalence points. So you can estimate the first Ka and the second Ka. The strength of an acid or base refers to what extent it dissociates. The more it dissociates, the stronger it is. And the stronger the acid, the weaker its conjugate base will be. Since Hi is a very strong acid, I negative is a very weak base. Remember, according to Bronsted and Lowry, the better a base is, the better it will be at attracting protons. And I negative, Cl negative, they do a pathetic job of attracting protons, which are H plus ions. When comparing the strength of organic acids, look for very electronegative atoms, like fluorine. The more electronegative the atoms in the organic acid, the stronger it will be. Also, the more oxygens in the acid, the stronger it will be. Strong bases have extremely weak conjugate acids, while the most common weak bases contain both nitrogen and hydrogen. If you see N and H in a formula, it's probably a weak base. Every acid-base indicator has a pKa, and that pKa corresponds to the pH at which the indicator changes color. When performing an acid-base titration, choose an indicator that has a pKa close to the pH of the equivalence point. So in a strong base, weak acid titration, your equivalence point is close to 9, so phenolphthalein would be a good choice. Bromothymol blue or methyl red would be a bad choice. As an acid-base titration progresses, different ions or compounds will predominate. Take this titration curve for a weak acid and strong base. We said earlier that at the half equivalence point, the concentration of the weak acid and its conjugate base will be equal. At any pH lower than the half equivalence point, the weak acid will predominate. At any pH higher than the half equivalence point, the conjugate base will predominate. At the equivalence point, the weak acid is completely gone, and the conjugate base is the only factor that affects the pH. At any pH higher than the equivalence point, the titration mixture is essentially a strong base, as the weak acid is gone and the conjugate base's influence is negligible. A buffer is a mixture of a weak acid and its conjugate base. Buffers are useful because they resist pH change. If you add some acid to a buffer, the conjugate base reacts with it and keeps it stable. Likewise, if you add base to the buffer, the acid reacts with it and keeps it stable. To calculate pH of a buffer, use the Henderson-Hasselbalch equation. The reason that a buffer works is that adding a little bit of acid or base to the buffer doesn't change the ratio of weak acid to conjugate base very much, so the pH doesn't change much. When using this equation, as long as you know 3 of the 4 values, you can calculate the other one. You might notice that as long as you're using the same compounds, if the ratio of conjugate base to weak acid stays the same, the pH does not change. So a buffer containing 0.03 molar sodium bicarbonate and 0.01 molar carbonic acid would have the same pH as a buffer containing 3 molar sodium bicarbonate and 1 molar carbonic acid. However, we use higher concentrations to produce a higher buffer capacity. That means those higher concentrations will be able to withstand a greater amount of acid or base without changing their pH value significantly. Since this buffer has more conjugate base, it will withstand more acid. If a buffer has more acid than conjugate base, it will be able to withstand more base being added to it. The solubility of some ionic compounds depends on pH. For example, magnesium carbonate dissociates according to this equation. It's not very soluble in water, but what happens if we lower the pH? Well, lowering the pH increases the amount of hydronium ions present in the solution. And those added hydronium ions will react with some of the carbonate ions, which essentially removes those carbonate ions from the solution. Le Chatelier's principle tells us that when we remove something from a system at equilibrium, the system will try to replenish whatever was removed. So some of that magnesium carbonate will dissolve, replenishing those carbonate ions. That means the compound gets more soluble as the pH decreases. That's Unit 8. I'm Jeremy Krug. Join me soon for my 10-minute review of Unit 9, which covers thermodynamics and electrochemistry. So we can review some more AP Chemistry together.